Hey everyone, welcome to this explainer. Today we're literally dissecting a super fascinating piece of code. If you've ever wondered how data compression algorithms actually work under the hood, well, you're in exactly the right place. We're going to examine a Go function called ZipString, and we'll break down its logic line by line, loop by loop, to see exactly how it manages to shrink strings down to a much more compact form. Let's get right into it.
So, here's our roadmap for today. We'll start with the core concept, run length encoding. Then we'll look at the outer loop jumper, the inner loop scout, a really cool ASCII math trick, trace the code, and finally, run a stress test. All right, section 1, the concept, run length encoding. Before we even look at a single line of code, what are we actually trying to achieve here? Well, the ZipString function tackles a classic computer science problem, run length encoding. Basically, this is just the process of counting consecutive identical characters in a string and replacing that whole sequence with just two things, the count and the character itself. So a string of 5 A's simply becomes the number 5 followed by the letter A. It sounds incredibly straightforward, right? But actually writing clean, efficient code to pull this off, that requires some pretty smart architectural choices. Okay, take a look at the entire ZipString Go function. Let's just take a second to look at the whole organism before we start slicing it up. It's relatively compact. We've got our result string initialization, an outer for loop, an inner for loop, a string concatenation step, and finally our return statement. But don't let its size fool you. Inside this compact little frame is some highly optimized logic. Moving on to section 2, the outer loop jumper. Now, look closely at the initialization of that outer loop. It starts with I equals 0, I is less than the length of s. Notice anything weird? Yeah, what's really interesting here is what's completely missing. If you're a developer, your brain is probably hardwired to expect an I++ right at the end of that statement. We are just so used to seeing loops step through an array or a string, one single index at a time. This missing increment totally subverts our expectations and sets up a fun little mystery right at the top of the function. Well, here is the solution to that mystery. Down at the very bottom of the outer loop block, we see I plus equals n. The index is actually being advanced manually. So here's why that's crucial. This lets the loop jump forward by however many duplicate characters were found. Instead of plodding along checking A, then checking the next A, then the next one, the outer loop literally skips over entire blocks of already processed characters. It's a jumper. It only resets itself when a brand new uncounted character shows up. Which brings us to section 3, the inner loop scout. Let's break down this inner loop's logic step by step. I like to think of it as a scout being sent out ahead of our main position. First off, it captures the current character at our current index I, assigns it to a variable c, and starts a counter n at 0. Second, it kicks off a for loop that looks ahead. It's checking if the character at position I plus n matches our captured character c. As long as it matches, and as long as we haven't fallen off the end of the string, it hits step 3, incrementing that count, n++. But the very second this scout hits a totally different character, or the string ends, boom, the inner loop stops. At that exact moment, n perfectly holds the total count of how many times that specific character repeated. All right, section 4, the ASCII math trick. So to actually append our findings to the result string, the code uses this specific line. Res plus equals string n plus 0 plus string c. The absolutely brilliant part here is the n plus 0 character. Think about it. The variable n is an integer, let's say the number is 3. But we need to add the actual text character 3 to our string. By adding the integer n to the ASCII character 0, the underlying math naturally pushes the ASCII value right up to the correct corresponding digit character. It converts the count into text instantly. Now, as the source material points out, this trick does assume our counts are single digits, from 1 to 9. But that works perfectly fine for typical run length inputs, where you don't have massive, endless blocks of the exact same character. Next up, section 5, tracing the code. And this brilliantly illustrates the algorithm in action. Let's trace the somewhat absurd string you young fellas. Okay, so at index 0, we see the character capital Y. The scout goes out, finds no duplicates, returns a count of 1, and 1y gets appended. The outer loop jumps by 1. Same exact thing for the O, appending 1o. But then, at index 2, we hit a U. Our inner loop scout runs forward, incrementing n until it hits 3. It appends 3u, and then our outer loop jumps by 3, skipping the other u's entirely and landing beautifully on index 5 for the n.
You can see this exact pattern perfectly executed again at index 9 with those 4 L's outputting 4L. By the end, the final zipped string reads 1Y, 1O, 3U, 1N, 1G, 1F, 1E, 4L, 1S. Pretty slick, right?
Finally, Section 6, the stress test.
Let's rapidly fire through some edge cases based on our source analysis to see how robust this really is. What if there are absolutely no duplicates at all? Well, the inner loop simply counts n equals 1 for every single character, giving each a prefix of 1. Flawless. What if it's all the exact same character, like AAAA? The outer loop runs exactly one time, n becomes 4, and it returns 4A. Beautifully efficient. What about an empty string? The outer loop condition is less than the length of s immediately evaluates to false, and it just returns an empty string. No errors, no panics. And finally, what about spaces or exclamation points? The logic treats non-letters identically to letters. They're counted and prefixed exactly the same way. The manual jumping in Scout's logic just handles the whole shebang super smoothly.
And that brings us to the end of our explainer. But before we go, I want to leave you with a final thought to ponder. We talked earlier about how the in plus in trick works specifically because it relies on single ASCII digits from 1 through 9. So, how would you modify this Go code if a character repeated, say 15 times, requiring a double-digit output? Think about it. It's a fantastic puzzle to test your understanding of everything we've just covered. Thanks so much for joining me on this deep dive into the ZipString solution, and I'll catch you next time.